Okay, let's begin question 13. Gardner is cutting off pieces of string from a long row of string. The first piece he cuts off is 128 cm long, and each successive piece is 2/3 as long as the preceding piece. So that's really just a geometric progression. What that means is, let's say that the length of each piece we denote it by UN. UN represents the length of each piece. So the first piece would be how long? 128 cm long, right? But then you have to add on, you need to scale it by 2/3 each time you cut. So that will just be power n minus 1, right? For the nth term, it will be the original, but then you have to times 2/3 times 2/3 times 2/3. You only start multiplying 2/3 from the second term onwards, so that's why you will be late by 1. So you have to minus 1 to the power. So let's see. The length of the nth piece of string cut off is p cm. Show that ln of p equals to the following. Okay, so they took the ln already, and I know that this is what they are referring to as p, un. Oh, so that means I have p equals to 128 multiplied by 2/3 to the power of n minus 1. If this formula is not clear to you, maybe I'll just list down a few examples. If let's say this is the first piece, it will be 128. If it's the second piece, it will be 2/3 of the original, so times 2/3. Then if it's the third piece, it will be 2/3 of the one preceding, which means that it will be U2 times 2/3, which is 128 times 2/3 times 2/3, which is 2/3 power 2. Oh, so you start to see the pattern. If it's 3 power 2, you have to minus 1. If it's 2, it's invisible power 1, so you have to minus 1. Then how about U4? It's the preceding piece length, which is U3, multiplied by 2/3, which will be 128 times 2/3 power 3. Right? So in general, if it's the nth term, it will be n minus 1 power. That's how I got here. So anyways, p equals to this expression. Then you notice that there's a ln, so you have to take ln on both sides. So ln of p equals to ln of 128 multiplied by 2/3 to the power of n minus 1. Now, when you take a ln of a product, what does it become? It becomes a sum. So ln 128 plus ln 2/3 to the power of n minus 1. Now, continuing on, I see that there's a ln 2 and there's a ln 3. But here I got 128. I see 2, I see 3, it's fine, but 128. How do I link it to 2 and 3 here and there? I realize 128, I can prime factorize. So if I prime factorize it, I think it is 2 power 7, right? Yes, definitely. Then you get ln of 2 power 7. What happens when you have a power? Can bring down. So it becomes 7 times ln 2. Plus, here you also have a power, so you can bring down. You get n minus 1 times of ln 2/3. Can we go a bit faster? Yes, ln 2/3 is actually ln 2 minus ln 3. Bracket times n minus 1. Add on 7 ln 2 at the front. Okay, then what do we do next? We got ln 2 multiplied by some an plus b, ln 3 multiplied by some cn plus d. I see ln 2, I see ln 2. Here only a single ln 2, so what should we do? Multiply out the n minus 1 into the bracket. So n minus 1 times ln 2 minus way n minus 1 times ln 3. Notice that I never try to multiply the ln 2 into the n and the negative 1, into the n and the negative 1. Why? Because I know that I need a single ln 2. Here I got 7 copies, here I got n minus 1 copies of ln 2 of ln 2. What can I do now? Factorize out the ln 2. So it's 7 plus n minus 1. I don't need the brackets anymore. And bracket around the entire thing, ln 2. When I say I don't need the bracket, I mean I don't need the bracket around n minus 1 anymore. Okay, minus away bracket n minus 1 ln 3. Then you can simplify 7 minus 1 is 6 plus n, or rather n plus 6 times ln 2 minus away n minus 1 ln 3. Then let's take a look at the requested formula. As a plus in between the ln 2 and ln 3. So here it's a minus. What should we do? Bring the minus inside. So we get n plus 6 times ln 2 plus negative n plus 1 ln 3. Okay, good. So now let's take a look. Ln p equals to an plus b times ln 2 plus cn plus d times ln 3. So this guy is your an plus b. That guy is your cn plus d. Okay, so therefore a is equal to 1, b equals to 6, c equals to -1, d equals to 1. Okay, good. And that is your ln question. Part 1 done. Now let's move on to part 2. 13 part 2 show that the total length of string cutoff can never be greater than 384. So that means that you want to show that the length of the rope, sorry, no. You first need to understand that the length of the rope is just equals to the sum of the length of each piece. So it's the summation of un from n equal to 1 to infinity. Or of course, if you don't like the letter n, you can use the letter r. Just need to be sure of what is your variable and what's your constants. In this case, maybe it's better if I use r. So what would it be? It will be summation of the 128 times 2/3 power n minus 1 from, sorry, not n anymore, change to r. Then r equals to 1 to infinity. So how do we calculate that? This will actually be the limit as n goes to infinity of that sum. Sorry, wait, no, we don't need to involve the limit yet. We can have a shortcut. You can factor out the 128, then you get 2/3 power r minus 1, sum from r equal to 1 to infinity. This guy here is a geometric series, right? Times 2/3 each time. First term being substituting r with 1. 1 minus 1 is 0. Anything power 0 is 1. So this will be 128 multiplied by a over 1 minus r. Right? The sum to infinity of an infinite geometric series. The first term is 2/3 to the power of 0, which is just a 1. And the common ratio is a 2/3. So 1 minus 2/3 is 1/3. 1 over 1/3 is just a 3. So 128 times 3. What do you get? Let's see. 128 times 3. 384. That's the sum to infinity, right? But the length of the rope, if you cut infinite times, that's impossible, right? You can't have an infinite number of pieces of rope, right? So that means that the length of your rope will actually be not equal, but rather less than the sum to infinity. So, but this guy equals to this guy, equal this guy, equal this guy, equal this guy, 384. So therefore, we conclude that length of the rope is less than 384. And then we get our answer. Yeah, show that the total length of string cutoff can never be greater than 384. There we go, never greater. Yeah, maybe we should put down a less than or equal. Actually, yeah, no equal. I think that should be fine. Moving on to part 3, how many pieces must be cut off before the total length cut off is greater than 380 cm? How you must show sufficient working to justify your answer. How many pieces must be cut off before the total length cut off is greater than 380? So total length cut off is really just total length cut off up to the nth piece. Maybe I should write this down. Total length cut off up to nth piece is just the summation of ur from r equals to 1 to n. And we need this total length up to the nth piece to be less than 3. Let me read the question again. Total length cutoff is greater than 380. Okay, so that means we need this to be more than 380. Then we can just sub in the ur with what we had, which is 128 times 2/3 to the power of r minus 1. R goes from 1 to n, more than 380. So how do we simplify the left-hand side? this is really just a geometric series. So maybe it's easier if I just divide by, factor out the 128 first. Okay, like this. And then I divide over. Now I'm dividing by a positive 128. That's why my inequality sign, I don't need to flip the direction. So this is that. And this is a geometric series. A equals to 2/3 power 1 minus 1, which is 2/3 power 0, which is 1. Common ratio is 2/3. Number of terms is from r equals 1 to n. So n minus 1 plus 1, which is n. Number of terms. Maybe I should put a capital N. So therefore, okay, no, I'll just put down number of terms. So that means that your formula for Sn would actually be, which is this guy, this is Sn. It will be first term multiplied by 1 minus common ratio raised to the power of number of terms, all divided by 1 minus the common ratio. Why do I keep saying number of terms instead of just n? Because let's take a look at a quick example. Let's say you have I don't know, let's say 5r maybe more like 2/3 power, let's just say it, r. In this case, if I take r from 3 to 7, the first term is what? 2/3 power 3, right? It's 2/3 power 3 plus 2/3 power 4, then power 5, power 6, then power 7. Then you want to multiply this by 1 minus the common ratio, which is 2/3, raised to the power of number of terms. In this case, 3, 4, 5, 6, 7 is actually 5 terms. Right? So you put down a 5. You don't just blindly copy the upper limit and you put down a 7 here. You have to count the number of terms involving by considering the limit. 3, then 4, then 5, then 6, then 7. Total is 5 terms. But what's a faster way to get the 5? It's the upper limit minus the lower limit plus 1. Upper, lower, then you plus 1. Then all divide by 1 minus the common ratio. Okay, that's how you use the geometric series formula. Okay, moving on to the actual question. So moving back to the actual question, we can now use the formula. So first term is actually a 1. Then you multiply by 1 minus the common ratio, 2/3, raised to the power of number of terms, and close bracket, all divided by 1 minus the common ratio. This is more than 380 over 128. 380 divided by 128. What do you get? 95 over 32. I just simplified the fraction using a calculator to 95 over 32. Then 1 minus 2/3 is what? Is 1/3. If you bring it on top, you actually get a 3 times. Right? So 3 times of 1 minus 2/3 power n, more than 95 over 32. At this stage, maybe I'll just divide by 3 first before I proceed to using a GC. I divide by 3 now. So I get 95 over 96. Do I need to flip the direction of the inequality? Don't need, because 3 is a positive number. Divide by positive, don't need to flip. Good. So now you have power n more than 95 over 96. Maybe instead of this expression, I will subtract 95 over 96 to the left. So I get this expression to be more than 0. Okay, then now I'll move on to the GC to figure out what's the smallest value of n that I need. Yeah, so here's the GC. Then you can change the mode back to function. Change it back to function, and then you can go to y equals. Then you key in the function. So bracket 1 minus 2 over 3 to the power of, what is the power again? N. So you use an x instead, and then you subtract away 95 over 96. Of course, I'm using the divide symbol. You can always go second, can press alpha, then F1 if you want to make it into a fraction. I think in my older model of the calculator, I cannot. Oh wait, I can do it. Alpha, then F1, and I can select number 1 to access a fraction. Then I can key in 95 over 96 if I want to. But this is also fine using the slash symbol. Okay, so now you can, instead of drawing the graph, I would press second and table. then I'll get a table of values. So you notice that they are all negative, right? What I actually need is this expression to be more than 0. So I need to keep on going down and down and down all the way until I eventually get to a number that is positive. Then you should realize that over here, it's progressing a bit slowly, right? A bit slowly. So we probably need to increase the number by a lot. So let's see. Oh, right. I realized I made a mistake over here. The power n. Right. The power n here. Why am I not getting answers that's more than 0? It's all negative in the GC. It's because of the power n here. This is correct so far, but here, I made a mistake. I accidentally wrote my bracket before my power n. Oh, so I should remove the bracket here. Close the bracket there. Power n is raised, is attached to the 2/3, and close the bracket. Okay. Makes a big difference. 2/3 to the power of n. That's the expression we want. Okay, so back to the calculator. So the mistake I made. Maybe I should have, I should have put a bracket there, then power x, then after that I close the bracket like this. I think this should be better, but with an extra minus sign here. Okay, good. Then after that, you can check second table. You see all these values? It's already positive. So maybe slightly before that. Oops. Slightly before. Oh, right. I can't move up anymore because my x equal 46 is my smallest value. Maybe I should start with a smaller value, let's say 20. Then I'll press second table. Check my table of values. Sorry, I forgot about this change I need to make. When I want to start from a smaller value of x, you see currently it's at 46 and I can't change it too much already. And I want to go a bit smaller. I can press second table set. And from here, table start, I can change the value to something smaller. Let's say I start from 10. Or then I press second table. The table will start from 10. Then you realize it's negative here. And as you change the value of x from 10 to 11 to 12, the corresponding y value changes. In particular, you want to pay attention to 11 to 12. From 11, when x is 11, or rather n is 11, you get negative 0.001. But when it changes to 12, it becomes positive. So this is the point where we are interested in. We want the value of n that gives me a positive value. So using the GC, you can tell that it must be 12 onwards. 12 onwards, then the value becomes positive. Right over here. 12. So go back to the screen. Back to the screen, and we get the smallest value of n is 12. So you just say using GC, use GC, n more than 12 or equals to 12. Sorry, starting from 12. So what is the final answer? How many pieces must be cut off before the total length cut off is greater than 380? So the answer is 12. 12 pieces. 12 pieces must be cut off. Okay. Let's take a look at question 14 now, part 1. Using the formula for sine A plus minus B, prove that sine R plus half theta minus sine of R minus half theta is equivalent to 2 cos R theta sine half theta. So the formula that you would want to use over here is sine A minus B, which is actually just sine A cos B minus cos A sine B. Now, this R plus half theta is the argument of sine r. So it really, if you write it in a different way, it's actually sine of r plus half, then times theta, like this, minus way sine of r minus half times theta, close bracket, right? Then, yeah, so you want to show that it's equal to the right-hand side. How can we do that? Just use the formula. So treat this as your A, treat this as your B. So you get sine minus sine. Okay. Maybe it's better if we distribute the theta in. Yeah. Then we end up with sine of r theta plus half of theta. Minus away sine of r theta minus a half theta. Now we can see the pattern. A plus B, A minus B. This is not A, that is not B. You have to use A plus B here and A minus B here. It should be a plus minus here and a plus minus here. Yeah. Okay. Can. Good. Then now we can use the formula. I think this will work. Sine of A plus B will be what? Sine A times cosine of B plus cosine A sine B. Then the next one, minus away, sine A cos B, minus away, cos A times sine B, which is half theta. Okay, distribute the minus and what do you get? Distribute the minus, what do you get? Get minus sine r theta cosine half theta. And the second term must become a plus. Must become a plus. Okay, then we can see that there are some terms that can cancel each other off. In particular, here and there, cancel off. Which means you're left with cosine r theta times sine half, cosine r theta times sine half theta. Then you add these two like terms together, you just end up with two copies of cosine r theta times sine half theta. And we are done. That's the right hand side. Okay. Sure. Or is it proven? Yeah, proven. Should be proven. Okay, next part. That was part one. Now moving on to part two. Hence, find a formula for the sum of cosine r theta in terms of sine n plus half theta and sine half theta. Okay, so cosine r theta, sine n plus half theta, and sine half theta. They look very, very similar to the first part. Oh, that's why this is a hence question. Where do you see cosine r theta? It's over here. It's over here. So maybe we should make use of that, right? Maybe we should make use of that. So let me just copy down the question first. And I should copy down the conclusion we have. From part one. So from here, how do we find out the summation from r equals 1 to n of cosine r theta? Now, cosine r theta, where do we get it? It's from here, this part. Then you can just divide by 2 and divide by sine half theta, and you can get cosine r theta as a subject. So that's what we're going to do. Cosine r theta will become sine of r plus half theta minus away sine of r minus half theta, all divided by 2 sine half theta. Now, this is a constant, right? 2 sine half theta, or 1 over 2 sine half theta. It's not related to r. That means you can actually factor it out. So 1 over 2 sine of half theta multiplied by the summation of the difference here. Sine of r plus half theta minus a sine of r minus half theta. R equals 1 to n. Here, these two are considered as variables because it involves R, which is controlled by the summation. Sort of controlled, huh? You can't get out of this summation because you need to replace it with R equals to 1 up to n. These R's make sure that they are trapped inside the summation. This 2 sine half theta is free from R, so that's why it can be factored out. It's treated as a constant. The theta here is also a constant. Sine of half theta is a constant. 2 times sine half, still a constant. Constant 1 divided by a constant, still a constant. That's why you can factor it out. Then what else do we want to do now? Whenever you see a minus and a summation, what do you think of? Method of difference. Okay, that's what we're going to do now. Yeah, so we're just going to replace each term one by one. Just to save some space, I'm going to move my equal sign a bit more to the left and multiply by square bracket here, square bracket there. I replace each value of R with 1, 2, 3, and n minus 2, n minus 1, and n. So let's do that. So we get sine of 1.5, that's 3 over 2 theta, minus sine of 1 minus half, that's 1/2 theta. Add on sine of increase by 1, so it's 5 over 2 theta, minus away sine of increase by 1, 3 over 2 theta, plus sine of 7 over 2 theta, minus sine of 5 over 2 theta. That's R equals to 1, R equals to 2, R equals to 3. Continue on, plus R equals to n minus 2, R equals n minus 1, R equals to n. Okay, let's just copy down the expression first. Copy and paste it here. Then you get what? You'll get a sine of, if R is n minus 2, you add on a half. What's minus 2 plus half? Minus 4 over 2 plus half, which is n minus, minus 4 plus 1 is minus 3 over 2. So it's it's just a sine n minus 3 over 2 theta. Is that right? No, that's not right. N minus 3 over 2 bracket times theta. Yes, that makes more sense. Just to make it look nicer, I'm going to draw my bracket slightly bigger. Then subtract away sine of, in this case, if I sub in n minus 2 minus half, I'll get n minus 5 over 2 bracket times theta. Okay, then now you add on the next copy of sine. So you just have to sub in n minus 1. The pattern here to note is you're increasing the value of R by 1 and the value of R by 1. So that means that you have to plus 1 to that coefficient in front of theta. So minus 3 over 2, you plus 1 to it, what do you get? Minus 3 over 2 plus 1, you get minus half. So n minus half, bracket times theta. Minus sine of, at 1, what do you get? You get minus 3 over 2, bracket theta. Okay, and on the next one, the last one, when R equals to n, so you get n plus half. Theta minus away sine of, substitute the R with n. So you get n minus half. Theta. Okay, I'm just basically using this formula and substituting R with n minus 2, n minus 1, and n. One by one. Then what do you realize? Anything to cancel? Yes, this one, this one, this one, this one, this one, and this one. You're left with the top half, the bottom half. Then what is this equal to? This will be equal to 1 over 2 sine of half theta multiplied by, copy and paste the remaining terms. There's a minus sine half theta. There's a plus sine something theta. Okay. And then you multiply, and you're just drawing the square bracket. Oh, okay, good. So that's the expression. Does it answer the question? Let's read the question. Day 1, in terms of sine n plus half theta and sine half theta. So we have answered the question. That's it. Done. Okay, any other questions? Yes, there's a part 3, but here it's proved by method of mathematical induction. This is no longer in the syllabus, so we can skip this. Okay, next question. The sum Sn of the first n terms of a sequence U1, U2, U3 is given by the following. So let's just copy it down. Sn equals to what? N multiplied by 2n plus c. So c is a constant. Part 1 asks you to find un in terms of c and n. So straight away, you must know the formula, Sn minus 1. So you just take n times 2n plus c. That's Sn. Subtract away. Sub in n with n minus 1. So n minus 1 multiplied by 2 times n minus 1 plus c. Close the bracket. Okay, expand this out. What do you get? You just get 2n squared plus cn minus away. Maybe I'll just multiply in the bracket first. So 2 times n minus 1 squared plus c times n minus 1. So 2n squared plus cn minus away 2 times n minus 1 squared minus away c times n minus 1. Then now I can continue simplifying. The n minus 1 squared open up, you get n squared minus 2n plus 1 minus away c times n plus c times 1, which is plus c. So 2n squared plus cn minus 2n squared plus 4n minus 2 minus cn plus c. Anything to cancel? Yes, 2n squared minus 2n squared. Anything else? Yes, cn minus cn. And finally, we are left with 4n minus 2 plus c. Okay, that's part 1. Moving on. Part 2, find a recurrence relation of the form un plus 1 equal f of un. Now, this is technically no longer in the syllabus, so we are gonna skip this one. Okay, recurrence relation is no longer in the syllabus if you want to find the explicit expression. But we can still try. Right? Yeah, why not? Okay, so un plus 1, you want it to be a function of the previous un term. So how will we do it? You need to figure out what's un plus 1 first. So un plus 1 is what? It just means you take everywhere that you see a n from un, but replace it with n plus 1. So you get n plus 1 here, minus 2 plus c. Expanding it, you get 4n plus 4 minus 2 plus c. Now, I know 4 minus 2 is just a 2, but that's not what you want to do. What you want to do instead is to see how you can relate this to un. I see that there's a 4n minus 2 and a plus c. So that just means that I can rewrite this as 4n minus 2 plus c, but add on a 4, which means that this is just un, right? I can recall that this is just un, right? This guy is un. So I can substitute 4n minus 2 plus c with un, and then I add on a 4. Then that's your formula, expressing un plus 1 in terms of un. This is technically no longer in the syllabus, so you can ignore this part. Just figure out how to find un. Remember the formula, Sn minus 1. Next question, 16. Prove by MI the following. So again, we can skip this because this is not in the syllabus. So moving on. Proof by method of difference. This is in the syllabus, that the summation of this guy equals to the following. So you need to know straight away that 1 over r times r plus 2 is just a geometric series. Sorry, it's just a fraction that can be decomposed into partial fractions. So a over r plus b over r plus 2. Cross multiply, we get 1 equals to a times r plus 2 plus b times r. Okay, so good. So now we can just sub in r with negative 2. We get 1 equals to 0 minus 2r. Minus 2b, sorry. That means that b is equals to negative half. Or we can sub in r with 0. We end up with 1 equals to 2a plus 0, which means a equals to half. So a here is 1/2, b here is negative 1/2. Then therefore the summation of this 1 over r times r plus 2 will just be equals to the summation of each term. So half over r, or maybe I can make it look nicer. This will be 1 over 2r minus away 1 over 2 times bracket r plus 2. So 1 over 2r here minus away 1 over 2 bracket r plus 2. Then now you fill in the limits, r equal to 1 to n, r equal to 1 to n. Now, every time you see a minus sign followed by a summation, you know you need to use method of difference. Sub in the first three, sub in the last three. So 1 over 2 times 1 is just 2. Minus away 1 over 2 times 1 plus 2 is just 3. It's r equal to 1. And now r equal to 2, add on 1 over 2 times, maybe I'll just put bracket 1 for emphasis. Next is 2 times 2, minus away 1 over 2 times 4. Yeah, next, when r is equals to 3, we get 2 times 3 here, minus away 1 over 2 times 3 plus 2 is 5. Add on dot dot dot. R equals n minus 2, r equals n minus 1, r equals to n. So what we get? Plus, 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 1 over, 1 over, 1 over, minus, 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 1 over, 1 over, 1 over. You can fill in the blank. So remember the formula, it was 2r. Okay, let me just copy it down. It's 2r on the left, so 2 times n minus 2. Then 2 times bracket r plus 2. So it's just 2 bracket n minus 2 plus 2 is just n. Okay, then after that, you just have to add 1 to it. So 2 times n minus 1, 2 times n plus 1, 2 times n, 2 times n plus 2. Inside the bracket, plus 1, plus 1. Inside the bracket, plus 1, plus 1. Okay, good. So that means we can start to compare, close the bracket first. Let's start to compare. Oh, right, there is no coefficient, so it's fine. You don't need to close the bracket. Let's start to compare and see if there's anything to cancel off. Let me see. Plus 2. So here, because there's a plus 2, if you try to expand this out, you actually end up with 2r plus 4. So that means that you are actually going to cancel off, you're actually only going to start cancelling off like terms, but opposite signs when it's 4 terms, around 4 terms away. So here I see minus 1 over 2 times 3 and positive 1 over 2 times 3. This pair cancels off. So notice that I had to travel a bit of a distance, this, in order to reach my opposite, in order to reach the opposite to cancel off. So likewise for the 1 minus 1 over 2 times 4, you also need to travel a bit to the next term in order to cancel off. But eventually they will still cancel off, so it's fine. It's just a little bit further away. This one also will cancel off. This one also will cancel off. 1 over the minus 1 over 2n will cancel off as well, like this. So this two will cancel off, and then eventually, what are you left with? You realize that you're not just it's not just 2 terms that remain. This is wrong. It's actually first 2 and last 2 that remain. So 4 terms that are remaining in total. So now let's just summarize that. It's 1 over 2 times 1, which is half, plus 1 over 2 times 2, which is 1/4, minus away 1 over 2 bracket n plus 1, minus away 1 over 2 bracket n plus 2. Okay. Then what did they ask for? Let's see. Show by method of difference that you will get this guy. 3/4 minus 1 over 2n plus 1 minus 1 over 2n plus 2. Are we there yet? Almost. Half plus 1/4 is 3/4. The other 2 fractions, is it the same? Yes, it's the same. So we are done. We are finally done. Proven by method of difference. Okay, moving on. So now part 2, maybe this is part, I should label part 2, part A. Then now we move on to part 2, part B. Explain why this sum is a convergent series and state the value of the sum to infinity. Okay, so let's see. Actually, you can just take the limit of this expression, but you replace the infinity with n and introduce lim n goes to infinity. That's good enough an explanation already. So let's just do that. So part 2, part B, what would it be? It will be summation of 1 over r times r plus 2 from r equals to 1 to infinity. But this is exactly the same as replacing the infinity with an n, and you take the limit as n goes to infinity. Limit as n goes to infinity of this summation is really just the expression that we have found from part A. So replace that. Then after that, you must consider what happens as n goes to infinity. What happens to this fraction? This n goes to infinity. So n plus 1 becomes even bigger, 2 times even bigger. So the denominator becomes very, very big. 1 over very big is actually just a 0. Likewise for the other guy, 0. But the 3/4 is not affected by n, so it's just 3/4. So final answer is just 3/4. Okay, and the reasoning is because of the limit. These two terms go towards 0. Another way to write this down would be to say that 1 over 2n plus 1 bracket approaches 0. And if you put a negative, it's still approaching 0. And negative 1 over 2 bracket n plus 2 also approaches 0 as n approaches infinity. Then this means that as n approaches infinity, the 3/4 minus 1 over 2 bracket n plus 1 minus 1 over 2 bracket n plus 2 approaches 3/4 minus 0 minus 0, which is equals to 3/4. But this left-hand side is what? This left-hand side is the sum to infinity. So that means that the sum from r equals to 1 to infinity of 1 over r times r plus 2 will be equals to 3/4. That's another way you could explain this using the arrow symbol. Tends towards. You read this as tends towards as n goes to infinity. Okay, that's part 2, part B. Next, question 17. Show the following. This plus this plus this equals a over n cubed minus n. Now you can either do partial fractions and work from left to right, or you could just add the fractions together to get the a. So let's just do that. So 1 over n minus 1 minus away 2 over n plus 1 over n plus 1 equals to a over n cubed minus n. This right hand side, we can just ignore it for now. We'll come back to it later. Just combine this into a single fraction. So it's n minus 1 times n plus 1. So what do we get? This guy must be n times n plus 1 minus 2 times n minus 1 n plus 1 plus n minus 1 times n. Yeah, correct. And simplifying, we get a minus b times a plus b is just a square minus b square. So n square minus 1 square. 1 square is just 1, so we drop that square times n. What do we get for the denominator? Oh, n squared times n is n cubed, minus 1 times n is n. N cubed minus n, which looks exactly the same as what we require on the right-hand side. Okay, so we're on the right track. How about numerator? Now we have to simplify. So just expand everything out. N squared plus n minus away. This times this is n squared minus 1 square, which is just a 1. Then negative 2 times into n squared minus 1, which is negative 2n squared. And then positive 2. Okay, then after that, this one n times n minus 1 times n. You get plus n squared minus n. Okay, anything to cancel off? N minus n cancels off. Okay, good. So n squared minus 2n squared plus n squared also cancels off. So you're left with a single 2. So therefore your answer A is equals to 2. Okay, that's for part 1. Moving on. Part 2, hence find this sum 1 over r cubed minus r equals to 2 to n. There is no need to express your answer as a single algebraic fraction. Can. So you realize that this and this look very similar? Yes, the n basically got replaced with r, and then you take the summation from r equals to 2 to n. Just treat n as a constant number. So yeah, we're gonna make use of that formula now. So in part 2, the summation of 1 over r cubed minus r, where r goes from 2 to n. This is really just, if you multiply by 2, and then you divide by 2 again, you realize that they will still stay equal. But why did I do that? Times 2 divided by 2. Oh, divide by 2 is the same as times half. Reason being, this part here and this part here look the same, which means that I can use the formula from part 1. That's what makes this a hence question. You can use the answer from part 1. So 2 over r cubed minus r is really just this 2 over n cubed minus n, but replacing the n with r. So I will just have to copy and paste this formula, but replace the n with r. So I'll just do that. Let me change the n to r first. Then I substitute in, and then I take a summation from r equals 2 to n times half in front. Now, you can continue simplifying this, but it's really just method of difference. You don't need to use any special identities, just manually substitute. So don't forget the half in front and square bracket, sub in, r equals to, take note, we don't start from 1, we start from 2. So it's 1 over 2 minus 1, which is 1, minus 2 over 2, plus 1 over 2 plus 1, which is a 2 plus 1, which is a 3. Yeah, this is r equals to 1. Next, if r is equals to 2, we add on. So we just add 1 to all the new denominators. R equals to 3, do the same thing. Just add 1 to the numerators. Make sure you write it neatly so that all of the minus, plus sign, and the numbers are along the same column, so that when we cancel off later, it will be easier to see the pattern. Plus dot dot. Then next, last 3 terms, n minus 2, n minus 1, and n. So plus 1 over, if r is n minus 2, we will get the following: n minus 2 plus 1, n minus 1. Okay. Then next one will be n minus 2 over n minus 1 plus 1 over n. Then it will be n minus 1 minus 2 over n plus 1 over n plus 1. I am simply replacing this formula here in terms of r with n minus 2, n minus 1, and n respectively to get those 3 expressions. Okay, then we can start to see anything that cancels off. Oh, don't forget to close the square bracket. There's a half times in front. Anything to cancel. Let us see. Here, plus 1/3 minus 2/3 plus 1/3 again. That just cancels off, right? Because this makes up 2/3, that's a negative 2/3. So we can cancel them off. Likewise, you have a plus 1/4, minus 2/4, and a plus 1/4 that's not written down when r is equals to 4, but we don't have to write it down. We know it's there, so we just cancel off. Everything else, 1/5 also can cancel off with some other minus 2/5 and a plus 1/5 somewhere else. So eventually everything else will cancel off. This one will have a third term cancelling off. Then this plus 1 over n minus 1, minus 2 over n minus 1, and plus 1 over n minus 1 will also cancel off. They come in triplets, triplet. Then what am I left with at the end of the day? I'm actually left with this part here and that part there. What you realize is that these 2 parts are no longer just single terms. There are 1, 2, 3 terms at the top, 1, 2, 3 terms at the bottom. So have to be careful in this kind of situation. This is still method of difference, but now with 3 terms. Okay, so sub in, so just simplify it down. You get half multiplied by, let me just copy down the triangle. and the other triangle. Okay, and the close bracket. Okay, good. Just to make it look neater, I'm just going to rewrite it. So it looks like half minus 2/2 plus half. Move the bracket away to make space. Plus 1/n minus 2/n plus 1/n plus 1. Oh, okay, good. So this is equals to half multiplied by, let's see, what's 1/1 minus 2/2? It's just a 1, so they cancel off. You're left with a single half plus 1/n minus 2/n is just minus 1/n. Then plus 1/n plus 1 is just 1/n plus 1. Close the bracket. Now combine, now just multiply out the half. You will get 1/4 minus 1/2n plus 1/2 times n plus 1. Okay, I think that's simple enough. They requested us to not leave it as, you don't need to leave it as a single fraction. So this is fine. Okay, can. That's part 2. Moving on. Give a reason why this series converges and write down its value. Okay, can. So what we need to do is to realize that this sum from 1 to n, from part 2, let me just summarize what we have from part 2. From part 2, this is what we have. This is part 3. Then we can mention this is from part 2. That means that we can now consider the sum to infinity of r cubed minus r. It's just the limit as n goes to infinity of the summation from r equals to 1 to n of the left-hand side expression 1/r cubed minus r. But we know this guy. It's just the answer from part 2. So copy and paste, and then you take the limit as n goes to infinity. So what happens? This guy, 0. This guy, 0. Why? Because the denominator gets very, very big. 1, which is very small, divided by a very big, will approach 0. Likewise for 2 times n plus 1. Even worse, from n upgrade to n plus 1, it becomes even bigger. So the denominator is even bigger, and you have a small on top. Small divided by big. And the big is very, very big. It will just go towards 0. Okay, so therefore at the end of the day, you are left with 1/4, which is not affected by n. N gets bigger and bigger, 1/4 stays as 1/4. But the other guys go towards 0. So it's minus 0 plus 0. Of course, it's just 1/4, and that's your final answer. Okay, moving on. I believe that's all. Yeah. Okay, moving on. So now we got question 18. Use MI to prove the following. So this one again, not in the syllabus, so ignore it. But we can use this as pretend that it's already proven and just use it. Now find the summation of r squared from r equals to n plus 1 to 2n. This one has to be a bit tricky. You have to be a bit tricky here, because what we have now is a formula that goes from 1 to n. Maybe it's still useful. Okay, it will only be useful to us if we make sure the denominator, sorry, not denominator, the lower limit here for r is 1. Here it's not 1, it's n plus 1. So what can we do? We actually need to split it up like this. R equals to 1 to 2n, and then subtract away sum from r equals to 1 to just before n plus 1 is n. Correct or not? So let's say, for example, if I don't use such complicated n plus 1 and 2n, I use, let's say, 5, maybe not so big, 3 to 5 of some happy face sub r. Okay, let's not use a happy face. Let's just use an actual expression. Let's say 2r. Okay, good enough. Then what is this equal to? It means you sub in r with 3, sub in r with 4, sub in r with 5, right? But isn't this just the same as taking this entire expression, I copy and paste it, I add and subtract. I add on 2 times 2, add on 2 times 1. Then at the back, I subtract 2 times 1, subtract 2 times 2. Right? They will cancel each other off. So it stays equal. But of course, you don't try to cancel it off. What you should realize is that these first two guys I added is just the r equals to 1 and r equals to 2 terms. And these two guys that I subtracted away can actually be rewritten as minus away the summation of 2 times 1 plus 2 times 2, which is really just r equals to 1 and r equals to 2 of the sum. So that means that I can actually rewrite the first 5 terms as the summation from 1 to 5 of the same expression 2r, but then I subtract away these first two guys, r equals to 1 and r equals to 2 terms. So r equals to 1 to 2 of 2r. Can you see the pattern? 1 to 5, subtract away 1 to 2. Then I'll be left with 3 to 5. More simply, index 1, 2, 3, 4, 5, take away index 1 and 2, you'll be left with index 3, 4, 5. Does that make sense? Okay, so that's what we're going to do here. Just split 2n and n plus 1 up into 1 to 2n, then take away 1 to n. Just 1 before the n plus 1. Oh. This guy is just 1 before the 3. 1 less than 3. Okay. In order to get 3, we need to subtract away from 1 to 2, where 2 is 1 less than 3. 3 minus 1 gives you the 2. Oh, n plus 1 minus 1 gives you the n. Okay, good. Then that means we can just write down the expression here, and we can proceed to use the formula. Just need to take this formula, sub in, instead of n, it now becomes a 2n. And for this guy, it is literally the same thing. So you can just copy down, word for word, 1 over 6 times n plus 1 times 2n plus 1. Then you simplify it. They need a fully factorized form, so yeah, we have no choice. We need to factorize it. So let me just move this aside, and we will carry on with the question. So paste this here for reference. Then we take the sum from 1 to 2n. That means we just replace everywhere we see n with 2n. Here, if we replace the n with 2n, you get 2 times 2n plus 1, bracket, which is 4n plus 1. So 4n plus 1. Then minus away, copy word for word. 1 over 6n, n plus 1, and and 2n plus 1. So we need to factorize. I see there's a 1, 6. So we can factor that out. I see there's a 2n plus 1. We can also factor that out. I see there's a n, we can factor that out. So 1 over 6 times n times 2n plus 1. Factor out, I'm left with 1 over 6 here, n goes here, 2n plus 1 goes here. You're left with 2 and 4n plus 1. 2 times 4n plus 1. 1, 6 goes here, n goes here, 2n plus 1 goes there, and you're left with a n plus 1. So minus away bracket n plus 1. 1 over 6 times n times 2n plus 1, close bracket, times 2 times 4n is 8n, plus 2 times 1 is 2, minus away n, minus away 1. Simplify a bit more, 8n minus n is really just 7n. 2 minus 1 is just plus 1. Okay, then we get our final answer. Okay, now we got question 19. It's similar to one of the previous questions, so let's just do it. So we got a geometric series here. They tell you if it has common ratio R, arithmetic series, and then another arithmetic series has first term A, common difference D. So I'll just denote them as maybe I like UN for my AS, sorry, my arithmetic sequence, not my series, and TN for my geometric series. Geometric sequence term, each nth term of a geometric sequence. So in the arithmetic sequence, I have A plus n minus 1 times D. For my geometric, it will be some first term p multiplied by common ratio r to the power of number of terms n minus 1. Just take note that the n here in these two tn's and un, they are just a running variable. They're just an index number, so they are not exactly related to each other. Don't go and substitute. Don't go and make n a subject and try to substitute in. No. So what else did they tell us? They told us the first three terms of the geometric series. Okay, first three terms, so T1, T2, and T3. Let's just write that down. T1 equals, T2 equals, T3 equals. P times r power 1 minus 1 is 0. So r power 0, which is 1. P times 1 is just P. Next is P times r power 1. Then next is T3, which is P times r power 2. Okay, good. Those are the first three terms of the geometric series. And they are equal to the first, fourth, and sixth terms, respectively, of the arithmetic series. So it will be U1, U4, and U6. Right? First, fourth, and sixth term. Good. So we just have to substitute in n with the corresponding value. You get an A, you get an A plus 3D, you get an A plus 5D. Okay, good. And these are equal to each other. Equal. So show that 3r squared minus 5r plus 2 equals to 0. So what we should do here is to equate the common difference. The previous question, what we did was to take the ratio between the geometric series, so T2 over T1 equals to T3 over T2. That's what we did. But here it would be better if, yeah, actually the method is still the same, sorry. Yeah, that's the key idea. They're still equals to a common ratio, T1, T2, and T3. So the ratio between T2 and T1, T3 and T2 is still equal to R. But of course, we don't directly substitute in with the expression for T1, the P, the PR, and the PR square for the T1, T2, and T3. Instead, we use its equivalent form, which is A plus 3D, and A plus 5D. And also just to take note, P equals to A. So actually, we can simplify it a bit. This becomes I'll use a different color. This becomes an A, that's an A, that's also an A. That's also an A. Just simplify it straight away. Then T2 over T1, what is that equal to? It's just A plus 3D. Sorry, don't need the equal sign here anymore. A plus 3D divided by T1, which is A, equals to T3, which is A plus 5D divided by A plus 3D. Is that right? Okay, good. Then what should I do now? Let me see. Okay, can. Then we'll just proceed to solve for A and D somehow. We can cross multiply, so we get A plus 3D bracket square, and A times A plus 5D. Multiply out, we get A squared plus 2 times A times 3D, which is 6AD plus 3D squared is 9D squared, equals to A squared plus 5AD. Anything to cancel off? Yes, the A squared cancels off. You're left with 6AD plus 9D squared plus 5AD. Anything else to cancel off? Take note that this is not set. This is 5AD. Bring it over, we get a minus. So we get 1AD plus 9D squared equals 0. Factor out of D, what do we get? A plus 9D equals 0. So factor times factor equals to 0 means the first guy equals 0, or A plus 9D equals to 0. Okay, can. So that also means that A equals to negative 9D. Is that useful? Maybe it's more useful if I make D the subject. So negative A over 9. Let's continue reading the question. You want to show that 3r squared minus 5r plus 2 equals to 0. I got an expression in terms of D and A's, but nothing involving R. By equating to the R, and then I substitute with the expression in terms of the arithmetic sequence, my r disappeared. My equation doesn't involve r. So what do I do now? I have to do the other way. Instead of equating to the ratio, right, I should equate to the common difference. I should equate to the common difference. So what do I mean by that? What I mean is, here we have a to a plus 3d, which is a difference of 3d. Here, a plus 3d to a plus 5d, which is common difference of 2d. So that means that if I take u4, I subtract away u1, I get 3d, which is equals to u6 minus u4. That will give me 5 minus 3, which is 2d. So I need to times 3 over 2 here to scale it back up to 3d. Right? This will give me 2d. I need to times 3 over 2 so that it becomes equal to 3d. But I also know that my u4 is what? My u4 is actually AR. So I get AR. My u1 is actually A, equals to, ignore the 3d in the middle. You have a 3 over 2 here, multiplied by, it's not 2d. Instead, you should realize that u6 is AR squared. Then minus away u4. But u4 is what? u4 is A plus 3d. No. It is actually AR. That's more useful. That would be more useful because we are trying to lead up to an equation involving R. Okay, so now let's continue. Let's just copy down our goal first before we continue, so we can stay on the right track. We need to eventually show that the equation boils back down to 3r squared minus 5r plus 2. So what's the odd one out? I see r squared here, but there's an extra a. Here is just a 3. I see 3 only. I see 3 here, but there's a divide by 2. So what should we do? We need to get rid of the a, we need to get rid of this 2. How can we do it? Maybe I times 2 first. So I get 2ar minus 2a equals to 3 bracket ar squared minus ar. Then multiply out, I get 3ar squared minus 3ar. I see that I have 3r squared. I want 3r squared, but I have 3ar squared. So what should I do with my a? I should divide by a, right? So maybe at this stage, not divide. I should just bring everything over to one side. So 3ar squared minus 3ar. Then these two terms bring over. I get minus 2ar plus 2a equals 0. Simplify. Minus 3ar minus 2ar is minus 5ar, and plus 2a equals 0. Anything else we can do? Yes, we can factor out a. Get 3r squared minus 5r plus 2 equals 0. Oh, factor times factor equals 0 means first guy equals 0 or the second guy equals 0. We have shown the question already. Shown. But here, a equals 0. Is that allowed? Can we have first term to be 0? Did they tell us any hints? A and D are non-zero. So that means that this guy is rejected. Impossible. Okay, so we have shown that equation already, but what's the point in doing that? The point is, part 2, deduce that the geometric series is convergent, find in terms of A the sum to infinity. We need to be able to use this equation to help us to factorize it to solve for R. Then we can deduce whether our geometric series is convergent or not. So let's just do that. Factorize this and we end up with what? 3, what was it again? Let me just check with a calculator. 3 minus 5 to 3r minus 2 multiplied by r minus 1 equals to 0. Okay, which means I'll get r equals 2/3 or r equals to 1. So now, can r be equal to 1? Can r be equal to 1? if r is equal to 1, this will not be convergent, but if r is equals to the other fraction 2/3, it will be convergent. But is there a way for me to deduce whether r should or should not be one of those solutions, so I can reject anything? I got it. R must not be equals to 1. Okay, this one has to be rejected. Why? One way that we can explain why is from this equation here. Recall that they also gave us the condition that A is not equals to 0 and D is not equals to 0. So you must obey this at all times. So suppose that R was actually equals to 1. If R is actually equals to 1, what will happen? It means that our AR here will be equals to A plus 3D. AR equals A plus 3D. But if R was equals to 1, then we get A times 1. So A will be equals to A plus 3D. Then that means that if I subtract A from both sides, I get 3D equals to 0, which means that if I divide by 3, I get D equals to 0, which contradicts with what was the required condition. D is not equal to 0. D is not equal to 0. Since there's a contradiction, we conclude that when R is equal to 1, we reject it. Reject R equals to 1. Okay, good. So yeah, this is gone. R is 2/3, which means that my geometric series is A times 2/3 to the power of n minus 1. I mean the sequence. In this case, I use the letter Tn, right? Yeah, Tn. Here the explanation would be, since the common ratio of the geometric series is 2/3 and modulus of 2/3 is less than 1, this implies that the geometric series will be convergent. The radius must be less than 1. Geometric series is convergent. Okay, good. Next. Okay, that was only part 2. Now part 3, the sum of the first n terms of the arithmetic series is denoted by s. Given that a is more than 0, find the set of possible values of n for which s exceeds 4a. Okay, let me copy down this question first. S. Okay. All right, so let me just bring this over here. So what we know is that the sum of the first n terms, so S is denoted by that of the arithmetic series. Right? So the formula for arithmetic series is what? N over 2 multiplied by A plus L. What is N over 2? I mean, what is N here? It's referring to the number of terms. So since they're asking about first n terms, that means this one is n. It's fine. If they say first m terms, then this will be m. But of course, that's not the case. They say n, so it follow through. Then A plus L, first term plus last term. What is the first term of this series, of this arithmetic series? Go back to the question. Arithmetic series, first term, it's just A. We denoted it by A. So let's just write that as normal A. Then what's the last term? It's the nth term. So A plus n minus 1 times D. I think that would be more useful here. Okay, good. So can we figure out what is A and D, given that we already know what's our value of R from part 2? Maybe. Let's see. Over here. Oh, by the way, this D has to be rejected because we already it was already given by the question D cannot equal 0. So D is equals to A minus A over 9, which we calculated from before, right? So we can use that. Let's just call this equation 1. So from 1, D equals to minus A over 9. What else can we deduce from this actually? Right. We have R equals to T2 over T1, which is the A plus 3D over A. So R equals to this fraction. I can copy it down as well. Then from here, we also know that R is equals to 2/3. Using these three information, we can solve for A and solve for D already, right? So let's see. Let me see. Yeah, okay. From this, we can deduce what's the value of A and D. So just substitute the R in, then we get 2/3 equals to A plus 3D over A. Then cross multiply, we get 2A equals to 3A plus 9D. Simplify, cancel off 2A on both sides, we get 0 equals to A plus 9D. Is that useful? Not really, no. Right. Okay, sorry. This information here is not that useful. The only useful information here is here. Information is this guy. Let's just read the question again. Sum of the first n terms of this arithmetic series, which we have found out over here, an expression for it, is denoted by S. Now, given that A is more than 0, so A is not 0, and it's positive, find the set of possible values of n for which S exceeds 4A. Exceeds 4A means it's an inequality. So what we should do is to say S is more than 4A, which means that we need the expression to be more than 4A. Now, simplifying this, we get n over 2 multiplied by 2A plus n minus 1 times d more than 4A. Now we can also multiply out the n over 2 into the 2A and into the n minus 1 times d more than 4A. Since A is more than 0, that means that we can divide throughout by A. Actually, the 2 and 2 cancel off. If I divide throughout by A, do I need to flip the direction of the inequality? Don't need, because it's positive. So I'll be left with a 4, something more than, then this is NA, right? N times A divided by A, which means you're left with an N plus N times N minus 1 times D over A. Okay, you just have to split into two separate fractions. And I happen to cancel off the A to leave behind the N. Now, this is very useful because I see that D over A. How can I link it to my equation 1? I realize. From 1, I can deduce that D equals minus A over 9, which means that D over A is negative 1 over 9. I'll call this equation 2. Then I can say substitute in 2. I'll get n plus n times n minus 1. The D over A becomes negative 1 over 9. Wow, no more D, no more A, just purely in terms of n, then I can solve for my set of values of n. So now I can multiply throughout by negative. So I get negative n, and this negative disappears, it becomes positive. But I still have a positive 1 over 9. Why do I multiply by negative? Because now I need to, okay, so after I multiply by negative, I can flip the direction of the inequality, get minus 4. I wanted to do that because I don't want to have a negative n square here. So let's just multiply out throughout by another copy of, by a 9, sorry, times 9 on the left and times 9 on the right. Since they're both positive, I don't need to flip the direction of the inequality. So I get minus 9n plus 9 times 1 over 9. Cancel off. You're left with n times n minus 1. Expand it straight away, n squared minus n. Less than minus 4 times 9, 36. So n squared minus 9n minus n is minus 10n, less than negative 36. Bring it over, become plus 36, less than 0. Then from there, you can use a calculator to help you to solve, or just solve the quadratic. What do I get? Oh, I get no real values. Something is wrong. Hi, sorry, I realized that there was a careless mistake over here. When you have a 2 here, you are supposed to continue bringing down the 2. So sorry about that. There should be an extra 2 here. Then I multiply everything else by an extra denominator 2. So over here, there's a divide by 2, divide by 2. Let's see. Multiply 12 by 9. I still have a divide by 2 here. Okay, I don't want this line. I'll just multiply 12 by a 2 as well. So I get minus 18n plus n squared minus n less than negative 72. N squared minus 19n plus 72 less than 0. Now we can try to solve. 1 minus 19, 72. You get less than 0, right? So that means it must be 5.227 approximately less than n less than 13.772. So what is the question asking us? The question is asking us find the set of possible values of n for which s exceeds 4a. So that means this is the set already. Of course, if you want to express it in a set notation, it will be the set of all n, an element of all real numbers, such that 5.227 less than n less than 13.772. Maybe we should round off to 3SF here, so it's 5.23, 5. And 13.8. 3SF. Correction, wrong. N is not actually a real number. N is referring to the number of steps after the value of a in the arithmetic series, right? Or the number of steps that you take after you start with the value a in a geometric series. You times r times r times r. How many times? Number of steps that you're taking, which is integer value, positive integer, maybe 0. So that means that over here, I should make a correction. It's not set of all real numbers. It should be integers. And since it's integers, it means that I can actually count the list down all the elements inside the set. So what are integer values that are more than 5.23 and less than 13.8? It will simply be 6, 7, 8, 9, 10, 11, and 12. That's the solution set. Oh. Okay, next question. Okay, now let's take a look at question 20. So what we have here is a sequence U1, U2, U3, ... all the way, such that U1 equals to 1. That's the first term when n equal to 1. And you have the following recurrence relation. All un plus 1 is in terms of un and some other expressions in terms of n for all n more than equal to 1. Now, using the method of mathematical induction, so this is no longer in the syllabus, you want to prove that un equals to 1 over n squared. So we'll just take it as a given. I'll assume that this is true. Then we carry on with the other parts of the question. In part 2, you want to find the summation from n equals to from little n equals to 1 until capital N of the fraction 2n plus 1 over n squared multiplied by n plus 1 bracket square. Now, where do you get this expression from? You realize it's over here, right? So you just need to make this guy the subject. So if you try to make this guy the subject, what do you get? So let's copy down the formula first. What we realize is we will need to bring this over and bring that over. So we get this fraction to be equal to un minus away un plus 1. Okay, good. So now we can substitute in this formula with un minus un plus 1. The limits stay the same, r equals to 1 to capital N. But what's un minus un plus 1? We have a formula here already. Un is 1 over n squared. So that means that I can replace my un with 1 over n squared. and my un plus 1 with 1 over bracket n plus 1 square. Take the sum from r equals to 1 to n. Oh, wait. Hold on. Let me see. It's not r, it's n. Sorry, the running variable here. Too used to writing r. Should it be a letter n? Must adapt accordingly to the question. Here they use letter n, we also follow with letter n. So now you just have to notice the pattern. You see a minus, you see a sum. What method do you use? Method of difference. Just manually sub in r, n in this case, not r, n equals to 1, 2, and 3, and then n equals n minus 2, n minus 1, and n. First 3 and last 3 terms. Strongly recommended to just write down step by step. Okay, let's just do that, and we will eventually get to. And we get this. Okay, so yeah, don't need square bracket here. And then we start to cancel things off. So this cancels, this cancels, this cancels, that cancels, this cancels, this cancels, and you're left with top cheese and bottom cheese. This Swiss cheese with a lot of holes in the middle. Chop off. Then you're only left with the top half and the bottom half. So simplify, and you get what? 1 over 1 square, which is 1. And then you subtract away 1 over bracket n plus 1 squared. Just have to manually key in, substitute in n equal to 1, 2, 3, n minus 2, n minus 1, and n. Yeah, so that is the sum. Hence, fine. Okay, part 2 is done. Let's move on to part 3. Give a reason why the series in part 2 is convergent. State the sum to infinity. Okay, same thing again. We just have to take the limit. For part 3 now. Take the limit of that expression, but this time we want the capital N to go to infinity because that's the variable now. And also I realized that I should be replacing with capital N minus 1. Sorry, let me make a correction here. Yeah, so replacing, the letter n shouldn't be letter n. Letter n is now a variable. It should be capital N minus 2, capital N minus 1, and capital N. So yeah, finally, I will obtain 1 minus 1 over capital N plus 1 bracket square. So yeah, then what is the question asking? We want to give a reason why the series in part 2 is convergent. Convergent just means that if you let the n, the variable, in this case, capital N, go towards infinity, we need to see it reach a specific value. In this case, I just have to replace the summation from letter n going from 1 to capital N with the expression we found from part 2. So capital limit as n goes to infinity. What do we get? So here 1 is not affected by capital N, so it just stays at 1. Minus away, take the limit of this fraction. If the denominator goes to infinity, infinity square is just very, very big positive. 1 over a big positive is just 0. So 1 minus 0, which is equal to 1. Okay, so that's why it is convergent. It converges to a value 1. Okay, that is part 3. How about part 4? Using your answer to part 2, all right, find the summation of 2n minus 1 over n square times n minus 1 bracket square, n equals to 2 to capital N. Okay, can. So this is what we want to find. They told us to use the answer from part 2. So that means if I just copy down the answer from part 2, I should be able to see some pattern. Let's see if there's any pattern. Here and there look very similar, right? You see 2n plus 1, you see n plus 1, you see 2n minus 1, you see n minus 1. What's the difference? What happens if I replace this n here with, let's say k minus 1? What will I get? Replace the n here with k minus 1. K minus 1. Let's see what happens. So the expression 2n plus 1 divided by n squared times n plus 1 bracket square will actually become 2 times k minus 1 plus 1 over k minus 1 bracket square times k minus 1 plus 1 bracket square. Simplify, we get this part here is 2k minus 2, then you plus 1, which is 2k minus 1, all divided by k minus 1 bracket square times k minus 1 plus 1 is what? Minus 1 plus 1 cancel off. You're left with just a k squared. A. Now you compare and contrast. Oh, it looks the same, right? Looks the same. It's just that now it's in terms of k versus in terms of n, but it's the same format. It's the same format. So we should do that as well. What we can do is to take this formula and replace the n with k minus 1. So that means my lower limit and upper limit will also change. It's a bit similar to integration. So if you start off with n equal to 1 and n equal to capital N as your upper limit, now you're doing the substitution. Let little n equal to k minus 1. So you get k minus 1 equal to capital N, k minus 1 equals to 1. Solving for k, you get 1. Sorry, you get 2. Solving for k, you get capital N plus 1. Oh, okay, good. So that means that in a conclusion, this answer from part 2, if we now substitute little n with k minus 1, we will end up with summation from n equals to the new lower limit. Sorry, it's no longer n, it's little k. With 2, upper limit being capital N plus 1. And this expression will change into this guy, which is the expression we actually want to reach at the end of the day, equals to 1 minus everywhere that had a little n, replace it with k minus 1. So little n eventually increases to capital N. So that means that you are, sorry, the upper limit is this n. So if the upper limit is now n plus 1, it will simply be 1 over n plus 1 plus 1 bracket square. Yes, correct. I believe so. Or would it not change? Let me think a little bit. Hi, sorry. So the final answer should not change. Sorry. Whenever you do a simple substitution here, only the expressions and the limits change. The final answer doesn't change. Okay, good. Can. So let's take a look. The final expression that we want to solve for is this guy, sum from n equals to 2 to capital N. Here we have a similar formula. It's just that the problem is the upper limit is no longer capital N, it's n plus 1. So what do we need to do? We actually need to split this up into 2. Sum from k equals to 2 to capital N. And then you add on the last term where you substitute little k with capital N plus 1. This is k equal to 2, 3 all the way to capital N. This is k equals to capital N plus 1. So let's substitute in capital K with n plus 1 now. And then we will get this expression, okay, equals to 1 minus 1 over capital N plus 1 bracket square. Now, we can simplify this expression here. So just simplify it. And what do we get? We will get 2n plus 2 minus 1, which is 2n plus 1. Okay, and then the denominator, we will get what? We will get n plus 1 minus 1, which is just an n square. 10 times n plus 1 bracket square equals to 1 minus 1 over n plus 1 bracket square. Now, take note, this guy is in terms of k, but of course, k is just what we call a dummy variable. You can actually change it to any letter you like. So just to make it look the same as the question, we can now replace it with the dummy variable little n that was used by the question. So we'll do that, and we will obtain sum from n equals to 2 to capital N of 2n minus 1 divided by. And just to make it look the same order as the question, replace the k with n. Replace k with n, dummy variable. Okay, so this will be equals to this fraction here, but you have to subtract away that k equal n plus 1 term. So you just bring it over with a minus sign. Okay, then that's your final answer. Of course, you can make it look nice by combining into a single fraction. Did they request for that? Well, they didn't request for it. I will leave my final answer as it is, like this. Okay, done.